All right, so we've talked about forces in one dimension, like with Newton's first law, when things are balanced or unbalanced with the net force pointing in one direction. We just talked about circular motion, where we have motion along a plane. In all these cases, Newton's laws are still valid. So this last little bit here, in this last lecture, I do want to talk about gravitation, and essentially gravitation on like a rotating Earth or rotating sphere. So this will apply to exactly what the rotation of the Earth or a planet does to gravity as we see it from riding along on the surface of the Earth. So with circular orbits, we got some questions that we should address here. So one question is, how does a satellite orbit the Earth? What keeps it up there? What forces are acting on it when it's doing this? Because normally we talk about gravity pointing inward, but we don't see a satellite fall back to Earth. We obviously see a satellite moving. So if this is our satellite, obviously it moves parallel to the Earth and doesn't fall down toward the Earth. So what is it that's actually keeping us from experiencing this if we're on a satellite or watching a satellite? And of course, why does it move? Why does it have to move in a circle? Why can't it be some other shape? All right. So to address these questions, let's define exactly what an orbit is. And we're actually going to do this. We're going to define this without actually using much math. We're just going to do a thought experiment. This is the same kind of thing that Einstein did. It sounds kind of dumb as far as like, oh, a thought experiment is just when you think really hard about something. But in essence, that's all a thought experiment is, but it can lead to some interesting insights. Okay, so for this thought experiment, let's consider a perfectly smooth, spherical, airless planet, okay, with just one big tower of height h on it. You can see we have that over here. We have our planet. We also have our tower here. I'll highlight in green. And it's got a height h, just like the thought experiment setup says. So that being said, let's assume a projectile is launched horizontally from the tower, okay? And if the launch velocity is small, then the flat Earth approximation, okay, so the flat Earth approximation is valid, and our classical 2D kinematic equations actually will work. Okay, and you can see what happens over here. This is going to be trajectory A. So I'll leave a note here, trajectory A. Okay, and we can actually see trajectory A. This object, this ball or whatever, leaves the top of the tower and hits, just a little bit in the horizontal direction away from the tower. And the idea here is that it traveled at such a short distance that we can assume that the Earth is flat and we don't have to worry about the curvature. Because clearly you can see in the image, we do have some curvature going on here, but it's just not enough to matter. So as we increase the speed of the ball or the object as it leaves the top of the tower, we notice that it keeps taking longer and longer for the ball to hit the ground. So if we jump over here to other trajectories, so you'll see here this B, this is a higher velocity. We can go to C. This is a really high velocity. So the idea here is that the distance that the projectile travels before finally reaching the ground increases because the projectile must catch up with the ground that's curving away from it. So essentially the idea is that because we also have this curvature, moving away from this projectile that's trying to get back to its initial height, because all objects, when we do flat Earth approximations, when you release them, they want to get to a vertical height of 0. Just like in all those problems we did where we fire a projectile, it always wants to get to the lowest point there. This will be our final height, the final height of 0 meters. So since we have to deal with the curvature of the Earth, clearly these objects are going to travel a little bit further. Now, in the special case where the launch speed is very large, then the curved trajectory of the ball is parallel to the curve of the Earth. So you can see here with trajectory D runs exactly parallel with the Earth. Okay, so in this case, the object continuously falls, but never hits the ground. Okay, and this is actually the definition of an orbit. So literally you can say this ball is so dumb that it tried to fall and missed the Earth, because that's literally what is happening right now. That's the definition of an orbit. So as far as orbits goes, the most important point of this whole qualitative analysis is that essentially an orbiting projectile is in free fall. So this is essentially a free fall problem, but we're not assuming a flat Earth over a small distance. Just like in free fall, the only force acting here is gravity. So this is just like free fall. Okay, so it's an idea that you're familiar with. Its tangential velocity is so large. So the thing that drives us into an orbit, or drives a particle or object into an orbit, is that initial tangential velocity. So it's got to be large enough that the trajectory actually matches the curvature of the Earth. Okay. And then when this actually happens, the object falls under the influence of gravity. But it never actually gets any closer to the surface because the surface keeps dodging it. Okay, so we can actually do some calculations with this. So an object in orbit around the Earth must have a centripetal acceleration that matches the acceleration due to gravity. Okay, so a centripetal acceleration that has to match the acceleration due to gravity. Well, we can set that up. We know how to set up a centripetal acceleration. That's just v squared over r. The trick here is it has to match g. Okay. Therefore, we can solve for this v orbit because that's the speed needed to actually get into orbit. When we solve this, we literally just simplify this equation. And it turns out v orbit equals the square root of rg. Oh, we've seen that before. Okay, so you should also note that, let's see, this doesn't depend on mass, which is weird. So the mass of the planet, mass of the object does not matter. So it's worth noting that mass is not included here. All right. So this is essentially the speed you need to orbit the Earth. If it's something greater, you might fall out of orbit and go into space. If it's something less, you're going to hit the Earth again. So of course, we can also calculate the period of a satellite, right? Because that's literally just distance traveled divided by the period. So this would be the circumference. Not necessarily of the Earth, because the satellite's a little bit higher. So this would be the circumference of the orbit. And this would just be the period, how long it takes to do one full revolution. But here's two basic pieces of information we can get, and it works pretty well to predict where satellites are and when satellites are. The next thing we need to talk about, we're going to talk about some fictitious forces, and then we're going to link this back to gravity and rotating Earth and what we're feeling while we're sitting on the Earth. So with fictitious forces, you can think about it sort of like watching a crash test dummy. So you can be inside the car riding along with the crash test dummy, or you can be outside the car watching as the whole thing unfolds. So a force throwing a crash test dummy into the windshield of a decelerating car cannot be identified. Now think about that. Okay, so it looks like there's a force throwing the crash test dummy, as you can see in this first image. It looks like there's a force that's suddenly just like pushing this crash test dummy into the window when the car stops. But remember, forces are action-reaction pairs, so there's an interaction. But really, you can't identify an interaction between the dummy and something else. So what's happening is it looks like there's a force there, but you can't identify the action-reaction pair or that interaction. So when this is the case, what we're seeing, if we're riding along inside the car, uh, remember this is the reference frame of the passenger. So when we're riding along inside the car, this mystery force makes it look like the dummy, which is at rest. So the dummy clearly at rest. It just starts moving when the car rapidly decelerates. Remember, this is a non-inertial reference frame. Okay. And that means Newton's laws are not valid. So the fact that we can't identify a force in our situation inside the car pushing this dummy through the windshield, that is okay because Newton's laws don't even work here anyways. So given that the car is decelerating, the coordinate system that we're talking about now, riding along with the car, like I said, is not an inertial reference frame. But we can fix this. We can say, okay, well, what if we put the reference frame outside the car? So here is our other reference frame outside the car. In this case, the reference frame outside the car is an inertial reference frame. Okay, so we're saved, and Newton's laws work if we're watching from outside the car. But the whole idea here is that in the ride-along coordinate system, so the one with the car, the whole idea there is essentially you're seeing things move around in your coordinate system, and there's not necessarily forces associated with those movements. However, these made-up fictitious forces, we can still use them to describe the motion in non-inertial reference frames. So you can think about like the Coriolis force. The Coriolis force is like the thing that causes intercontinental ballistic missiles to look like they're turning in their trajectory, things like that. Coriolis forces, really you can just describe that because as a particle moves long distances, as you can imagine the Earth, as a missile or something or a plane moves long distances over the Earth is still rotating under it. So even though the aircraft or whatever is traveling in a perfectly straight line, if we're riding along on the Earth, well, we don't see the rotation of the Earth, so it kind of looks like the plane or whatever is in the air for a long time. It looks like it's starting to shift. So even like the Coriolis forces are also an example of a fictitious force. So Coriolis force is also an example. Yeah, my apologies for using a meteorology reference. I am a meteorologist by training, so it happens. So let's think about some more of these instances where we have centripetal forces, or sorry, where we have fictitious forces. So when you turn the corner in a moving car, I'm sure you've all experienced this. So it feels like your body tries to it feels like you run into the door, or like the centrifugal force, as some people say, is like the thing trying to throw you out of the circle, but actually that's not quite what's happening. So when you do turn a corner, your body tries to continue moving in a straight line, just like if you were spinning a rock on a string and you cut the string, whatever direction the rock is pointed in that one instance. So you can imagine if you're swinging a rock, and if you were to cut the rope, so if we were to cut the rope, whatever direction the rock is at that instant, it's going to just continue traveling in a straight line. Okay, so same thing here in this car. So what's going on is the car starts turning, but your body obeys Newton's first law. Okay, your body obeys Newton's first law and wants to keep going in a straight line, and you can see that over here on this free body diagram. So even though the car starts turning, you in the car wants to keep going straight, which means quite literally the door, it sounds weird, but the door suddenly turns in front of you and runs into you. So only then, only when the car starts turning and you hit the side of the car, do you get that normal force from the door. And then the normal force from the door, that's what's going to keep you going along in the circle. That's your centripetal acceleration there, is that normal force. So the car's already started the turn, you haven't, and then you have to wait till you hit the door, and then that's what's going to start you going through the turn. Okay? So no, you were not thrown into the door. The door ran into you. Even though if you're riding along in the car, it may feel like some force is trying to throw you out of the car. That's just not the case. So this fictitious force is called the centrifugal force, not to be confused with centripetal. So this is not centripetal. Centripetal is real and it points into the circle. The centrifugal force is the thing that you feel. It gives you the sensation of being pushed out of the curve. So this is not centripetal. Don't get those two things confused because they're very different things. So this centrifugal force essentially occurs in a non-inertial reference frame. Because this happens, the thing you feel is in the reference frame of the car. So this is in the, wow, I can't write, in the frame of the car. All right, so we've talked about gravity, we've talked about centripetal and centrifugal forces. Let's talk about what this centrifugal force does to us on a rotating Earth when we're talking about gravity. So we often say that the weight of a person or object is simply the absolute value of the normal force. However, this assumes a flat and stationary Earth. So you remember the super easy free body diagrams. We have the normal force up, we have the force due to gravity down, mg, and the whole idea was like, oh, look, here if we sum the forces in the y direction, that's just the normal force up minus mg down. Therefore, the normal force equals mg. Okay, well, the normal force equals the weight down, and that's just their weight. So we're done. However, when we actually use this assumption, we actually get a value of g that's about 9.83 meters per second squared, and that's just doing this simple calculation under nice controlled conditions. But we've not been using 9.83. We've been using a value of 9.8 meters per second squared. So now the question is, why is the actual value of gravity slightly smaller than the, I'm going to say this in quotes, observed gravity, and this is in the case of when our normal force equals mg, if we were to calculate it that way. So the key here lies in the assumption of the flat stationary Earth, okay? This is what we are assuming when we use this simple calculation. All right, so let's take a closer look at what's going on when we try to calculate gravity for the Earth. Okay, so we want to find out where is this difference of, so I'm going to say a difference of 0.03 meters per second squared. Okay, so we want to know where that weird difference is coming from. Okay, well, first let's just think about this in some of the forces. We're on a rotating Earth. Okay, so we have gravity pointing in. Okay, so that's going to be positive pointing into the circle. But then we also have our normal force pointing away. That's going to be negative pointing out of the circle. And just for good measure, I'll switch this, do two different colors. So we have normal force pointing away. Okay. Now, let's just solve for the normal force, okay? We'll get this by itself, and that's easily done. So it turns out we just have our weight here, but look at this. So when we solve for the normal force, we have our weight minus, I'm going to use a third color. So we're subtracting from the weight, right? So weight, and then we have this term subtracted. So we have our total weight, mg, minus a little piece of that, okay? So it's reducing the weight by a little bit. So it turns out in the reference frame where we're riding along the Earth, okay, this term is actually a fictitious centrifugal force, okay, and it feels like to us it's trying to throw us off the Earth, essentially try to sling us off, and this term is essentially why measured gravity appears to be a bit weaker. All right, so the fact that we're measuring 9.8 meters per second squared instead of that 9.83 is literally because of the rotation of the Earth. So it doesn't change it by much, but there's a centrifugal force there in our reference frame. If we were watching this from space, if we were watching or trying to calculate weight from space, we wouldn't have to worry about it. But because this is a fictitious force in our frame, we have to come up with a way to explain it. And that, in our case, is just due to the rotation of the Earth. So that's just a short walkthrough of some tidbits from this chapter we've been in. Nothing too crazy. And as always, if you have any questions, please reach out and let me know. This pretty much ends the talk about Newton's laws and forces. So from now on, we're going to move into some applications of this, and then we're going to talk about work and energy in various systems.